This is Tech Math, if I could spell Tech Math. Oh, that's good. Tech Math 2. And we're in section 2-4, which has to do with circles. Alright, so if I had a circle, let's see if I can find a circle. There we go. Now I can have a circle. Oh, so I've got a circle. The circle has a center. From the center out to the edge of the circle, I have a radius. Going through the center of the circle from one of the sides to the other side, I have a diameter. So the diameter is going to be twice the radius. If I go and I have something that touches the circle in just one spot and no other spot at all, so I got a straight line. It doesn't really have to be a straight line, but it has to be, normally we think of it as a straight line, touching a point of the circle, no place else, then I have, that's called a tangent. So I'm tangent to the circle. If I have something that goes from one point of the circle to some other point of the circle without going through the center, so I'm hooked onto the circle both places, but I don't go through the center of the circle, that's a chord. La, that's a note, so that would not be a chord. Chord. And then if I have something that starts someplace else, goes through the circle, but doesn't go through the center of the circle, then that's a secant. And we say, well, those are cute words to be using, but you use tangent and secant someplace else when you do the trig functions. Why are you doing that for? Well, mainly it's just to confuse the student. So as long as the student's confused, that's all the math guy really cares about. So I have a circumference around the circle. So the circumference can be the diameter times pi, or it can be 2r pi, twice the radius times pi. That'd be the circumference. And then we have an area of a circle. Pi r squared would be the area of a circle, and that's the one we always remember, but we could put in a d there, so we could go pi d squared over 4. We could do that if we wanted to do that. We don't want to do that, but we could. Okay. Our picture is messy enough, so we'll go get another one. Alright, so I got a center, I got a point in the middle again. If I have an angle coming from the center of the circle, then that's going to be called a central angle. If I have an angle that's touching the circle someplace, like that, so now I got this angle right there, that's called an inscribed angle. Inscribed. Now, if they go on top of each other, so I got this circle guy, and I got a central angle doing this, and it's got some measurement, and then I got some inscribed angle That's going to the same spot like that. What do you think that angle is now? Yeah, I don't really know, but I'm sort of thinking it's half. I think this guy is 1/2 theta. Okay. If I have some circle, I got some circle, and it has some chord going from one side to the other, and I go from, I put a diameter in. Oh, we're not going to do that. We're going to go and put in a triangle. There we go. I'm going to put in a triangle with a right. That's a right angle. So I'm going to put in a triangle with a right angle. Well, that isn't going to be a right angle. I'll move back. Boom, boom, boom. If I have a circle, if I have a triangle inside a circle, and one of the sides of the circle goes through the center, and the other two sides of the circle are just touch the circle like that, then this angle has to be a right angle. Doesn't matter where I do it from or where I do it to. That's got to be a right angle. So whenever I inscribe a triangle inside a circle, and one of the sides go through the right angle's over here. We all knew that, didn't we? And the hypotenuse goes through the center of the circle, then I'm going to have a right angle. There we go. That's better. I guess that's probably enough. Page 97, 2 tangent lines drawn on a circle, blah, 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 segments, blah, blah, blah. All right, well, we'll see. All right, try to work some problems. Number 1. Why am I in green? All right, so find the circumference of the area. Okay. So all this is just another significant digit problem, right? So I'm given a diameter of 65.2 meters. Is that very far? Is that bigger than a football field? Not quite, but it's getting pretty close. All right, so circumference, d pi or 2 pi r. So we're going to go with 2 times 65.2 times pi, and when we get done, we're only going to keep 3 significant digits, and our calculator is probably set up for math type, so it's probably going to keep pi in it. So we'll look at the mode real quick. And my calculator is in classic, so that means it'll give me a decimal number, 2 times 25.2 times pi, and I get 409.66 meters, and 3 significant digits, 4, 10 meters, and that would be my final answer. And then my area would be pi r squared, 6 times 65.2 meters squared, pi times 65.2, 65.2. And I get 13355.036, and I ran out of room. But I'm only going to keep 2 significant digits, And so if I only keep two significant digits, 3. I'm only going to keep 3 significant digits, 1, 3, 4, 0, 0. Okay, next we're going to do number 4. I have a circle, and the diameter is 1,150 kilometers. 1,150 kilometers. Does that make it to Chicago? Yeah. Does it make it to Detroit? Maybe. Maybe Detroit. It doesn't make it to New York City, though. Okay, well, we want the circumference. Pi d. 1150 times pi. When I get done, kilometers will be my dimension, and I only want 3 significant digits. 1150 times pi. 3610. 3610. I want the area, pi r squared, or pi d squared over 4. All right, so we'll do that. Pi times 1150 squared divided by 4. I got 1038689.071 kilometers squared. 3 significant digits, 104, 0, 0, 0, 0. Put a comma there, put a comma there. Kilometers squared. I'm thinking that 1150 kilometers might be the radius of the moon. I'm thinking that that might be the case, but I'm not sure about that. Okay, we'll look at number 10, and we're going to go the other way. So number 10, find the diameter. I want the diameter given that the circumference is 245 centimeters. Okay, so circumference is pi d. So d is going to be circumference over pi. So 245 centimeters divided by pi. And when I get done, I only want 3 significant digits divided by pi. 78.0. 78.0 centimeters. 13 will be next. In the figure below, find the angle DEF. Okay, so obviously we need to start with a better than normal picture. So we'll start there. I don't know, make it a little smaller maybe. That's probably okay. All right, so now we're going to go and draw a line from here up to there, back to here, and then we're going to go from there through the center to someplace down here, and then we're going to come up to there, down to there. Am I okay? All right. A, B, C, D, E. Now, why did they make the center E? That doesn't make any sense at all, author. You should have made the center C for center. Okay, now, we've got this. And the arc A to B is 58 degrees. Okay, so over here we have 58 degrees going that way. All right, so that's good. And D to F. The arc going D to F is 40. Okay, so I got 40 over there. And then we want to find, oh wow, thank you very much. All right, so we want to find the angle DEF, the angle BDA, the angle CDF, and the angle BF, is it B? BDF. Okay, so that's what we're looking for. Okay. So what is it that we know? Okay. We know that this guy goes to the center of the circle, right? So that triangle, we know he's right. So that's the right triangle. We also know that this inscribed angle is half the outside. We know that. And so if that's 90 and that's 20, then we know that this guy down here is 70 degrees. So those are all things that we know. So with that, do we know anything we want to know? DFB. Is that DFB we want? DEF. DEF. Oh, DE. Do we want DEF? That's 40 degrees. Because the center angle is the same as the measure of the arc. So DEF. Okay, so that's good. BDA. BDA. Inscribed angle is going to be half that arc. So half of 58 is 29. So that'd be 29. All right, C, B, F. CBF. 20. I already got it. B, D, F. 90. Okay, good enough? Looks dumb. Looks might be hard. Might be hard, but it's not. All right, we'll do it again. We'll do it with 15. And number 15, we want figure 2.55. Okay, so we're going to put the circle on this side. Okay, and oh, this time the author has his act together. The center is marked C. Isn't that good? Yeah, about time, author. Okay, so we're going to go through the center out that way. We have something coming over to here, which is going to be tangent on both sides. Doesn't look tangent, but that's okay. And then we're going to come down to there. And then we're going to go there to there. Okay. A, B, C, D, E. Alright, so that looks good. Then we're being told that angle BAC is 30 degrees. Okay, so this guy's 30 degrees. Well, if that guy's 30 degrees, then the guy on the other side also has to be 30 degrees. If this angle is tangent, which it is, then that has to be a right angle. If that's a right angle, then this guy's got to be 60 degrees. What else do we know? That's about all we know, I guess. Well, we know this side over here, 120, if anybody should ask us that. Okay, if I had a construction line going that way, that's not going to do anything for me. If I had one going that way, that might do something for me. Okay, well, back to what they want us to find. BF, the arc length. BD, the arc length of the circle. EF, the arc length of the circle. Angle, ACB, angle, ADE. Right, so ADE, that would be nice to know. ACB, I already know that, that's 60. EF, where the heck did E and F go? Oh, F is there. So I got an F sitting here. So E to F. E to F. If this guy's tangent, then I have a construction line going like that, and over here I've got 60 degrees, so E to F would be that 60 degrees. Angle B to D, B to D. Okay, so that'd be 120. B to F, B to F, 60. So now we're working on A, D, E. A, D, E. Okay. All right, well, this guy's got to be 120 on that side, right? Because that's 60. This triangle has to be, this is an equilateral triangle because those two are the same, which means this angle has to be the same. So this has to be 30 and 30. 30, 30, 60, 180 degrees in the whole circle, in the whole thing, okay? And I want A, D, E. It's going to be 30 degrees. Good enough? No, not really, I know. All right, well, we will do 17. And so I got a circle, and I only have two. I got the center, and now I got to come out to there on tangent. I come over to here. Okay, because I'm tangent, I know that that's a right angle. Okay, and I'm given, this is 1756. Okay. AB is 68.2 centimeters. Well, first of all, I have to put ABC on. ABC. AC is 74 centimeters. Find the radius of the circle. Well, guys, I mean, really, it's a right angle, right? So the radius squared is equal to 68.2 squared plus minus, try again, 74 squared minus 68.2 squared. Okay, so R is equal to 74 squared. If the calculator was on, that would be a plus, minus 68.2 squared equals second function, square root second function answer, 28.7, okay, that'd be good, 28.7, 28.7 centimeters, So this is tangent, we have a right angle. Once we have right angle, we can do right angle stuff with it, which means Pythagorean theorem works. Okay, number 20. All right, find the area, find the perimeter. Now, I don't think I can do half circles. Okay, so what I'll do 2 circles. And then I'll hook them together. 2 circles, and then draw a dotted line there, a dotted line here, and then hook them together. Excellent. And I'm 38 feet diameter and 48.5 feet. Okay, so because I have this half circle on this side and a half circle on that side, I have a whole circle. So what I'm going to do is say I've got pi d for the circumference plus 2 times 48.5, and that'll give me the perimeter. All right, so pi times 38 plus 2 times 40, that's not a 4, 48.5. And I want, how many significant, 3 significant digits, 216 feet. Then I'm looking for the area, so the area is going to be pi r squared plus 2 times 48.5. Pi times r is going to be half, which is 19 squared plus 2 times 48.5. Boom. And again, I only want 3 significant digits. 1, 2, 3 feet squared. As I was saying, 1, 2, 3, 0 feet squared. A little small there. Okay, so that's number 20. We'll look at 21. Now, why am I doing 21? Well, I'm warming up for number 22. That's why I'm doing 21. All right. Find the area shaded. Okay, so I'm going to have the circle. I'm going to have something like that. I'm going to have something like this. I want the shaded area. This is 60 degrees. 60 degrees. Okay. Find the blah blah blah, the length of the inner radius. Okay, so the outer radius R1, R2. So R1, I'm going to go to there, and then R2 is going to be the big guy. Okay, so 36 feet and 20 feet. Now, how many degrees are there in a circle? 360. So 60 degrees of 360 degrees would be 1/6, right? So 1/6 of the circle is thrown away because of that cutoff. Okay, so if I go, I'm going to find the area of the shaded guy. So if I go pi, the big radius squared, minus pi, the little radius squared, I would find the area of the whole thing. Okay, and then if I multiply that by 5/6, then I would get the shaded area. So that's my plan. 5/6 times parentheses pi times 36 squared minus pi times 20 squared, close parentheses, boom. And I want 3 significant digits, 3 significant digits. Okay, so I would call that 2340 feet squared is what I would call it.
That would be 36 minus 5 times 20, right?
20 squared, right. Yeah. Because the area is pi r squared. So pi r squared is the area of the whole, and then I'm subtracting pi r squared, the center part. I'm subtracting that area, but I only have 5/6 of the total because I got a triangular thing taken out of it. Okay, now I've got 10 minutes to do problem number 20. I think last time when I tried to do this in 10 minutes, I didn't get it, but we'll see if I can do better this time. So I got some pedestal thingy. And what am I, 6 inches? So I got 6 inches, and then I got 16 inches, and then I got this circle that my picture is really bad, isn't it? I got this circle, okay, and then up here I got this right triangle that does that, and this is r minus 6, well that's obvious, and this is 8 inches. Okay, all that is obviously true. All right, so I'll find the diameter of the circle. Find the diameter of the circle. All right, well, how are we going to do that? Well, the radius squared of the circle is 8 squared plus r minus 6 squared, is it not? So that's the Pythagorean theorem of the thing. And then we could say that r squared is 64 plus r squared minus 12r plus 36. And then we could see that the r squares go away, and we could have 12r equal 100. Is that what it is? 100? And then r could equal 100 divided by 12. And then we want the diameter, so the diameter is going to be 2 times 100 divided by 12. Which would be 50 over 3. Would it not? Yeah. So we'll put 50 divided by 3 in our calculator, 16.6 repeating. So we'll call it 16.7 inches. Let's see, that's problem number 22. The odd ones aren't in the back of the book, right? The even ones aren't back there. So I must have got it right. Because you can't check it. Must be right.
Of course.
Yeah. Yeah, must be. 16. Yeah, that's you got the same thing? Well, yeah, I got the same thing because you did the same problem I was doing. But if the problem was set up wrong, then we both would have got the wrong answer, right? Yeah. So it's interesting that you can make your calculator do what my calculator does, but that still begs the issue of whether or not we set up the problem right. And is it reasonable that it should be 16.7 inches when this is 16? And I would say, yeah, that's probably reasonable. So we'll accept that our brilliant answer is correct because it is an even problem. So therefore, we can't second guess ourselves on whether or not it's right or wrong. And thus ends section 2-4.